We all know and love the Arduino Uno R4, a 32-bit Uno that packs a serious punch. Well, that's not one. Anyway, but while it's a great board, it's also rather large, which is why many have used their Nano versions of the Uno in the past. However, despite the amazing board that the Arduino Uno R4 is, because it's new, there's no Nano version of this board. Well, until now. That's right, Arduino have taken the Uno R4 Minima and shrunk it down into a Nano form, called the Arduino Nano R4. To demonstrate the very best of this board has to offer, we are going to create a miniature arcade machine that plays our own version of a very famous game. Space Attackers, Galaxy Invaders, something like that. Well, with all of that said, hello and welcome to this video for Electromaker. I'm your host, Robin Mitchell. Let's get to it. The prime feature of this video is the Arduino Nano R4, a nano version of the Uno R4, and let me tell you that this thing is far more capable than it looks. What makes this board extremely useful is that it takes the power of 32-bit computing and shrinks it down into a nano form factor that is breadboard friendly. Remember that the original Nano is an 8-bit machine, which is perfectly fine for many projects, but considering that the needs of modern technology are quite hefty, 8 bits just doesn't really cut it anymore. This 32-bit integration into a nano format means that complex projects requiring the hardware capabilities of the Uno R4 Minima can use the Nano R4 with no software changes whatsoever. In case you are not aware, that software compatibility is a big one. Now, of course, this doesn't have the same hardware like the LED matrix or Wi-Fi, but this is a nano version of the Uno R4 Minima, so you can't expect everything. Having said that, the lack of these extra hardware bits is what makes the Nano R4 so good. Not only does it reduce the price, it also reduces the size while simultaneously making it easier to use. So what is the Arduino Nano R4? It's a development board that puts the power of the Renesas RA4 M1 in a tiny package that can be used in prototyping and production. Since the headers are not soldered on by default and there are no components on the underside, you can directly solder this to a larger PCB or use it as is, making it highly adaptable. There is also a soldered version with the headers already present, but I got the one without. Despite not having all the same hardware that the Uno R4 Wi-Fi and the Uno R4 Minima have, the Nano R4 packs a lot of features. The first and most important is that it runs on 5 volts, making the Nano R4 5-volt tolerant. And why is this important? Well, there are plenty of reasons, but the two most important are that firstly, all your existing hardware will support this, including modules designed back in 1985 where 5 volts was all the rage. And secondly, this tolerance allows it to work with all previous Nano projects and circuits without any hardware changes needed. So let's say you have a Nano design that needs an upgrade. Well, just plug the Nano R4 and not only is it more capable in software, but the pin mappings and voltage levels all match perfectly. At the heart of this board is the Renesas RA4 M1, which is a 32-bit ARM core microcontroller that itself packs a serious intergalactic punch. It has 256 kilobytes of flash, 32 kilobytes of static RAM, and 8 kilobytes of EEPROM, all of which trump the first versions of the Nano. This increased memory size allows for far more complex projects, stacks, and better support for memory-heavy languages such as C++ classes. The CPU operates at 48 MHz, which is plenty for most projects, and an integrated RTC means that you can easily track time. When it comes to analog capabilities, the inclusion of a 14-bit ADC and a 12-bit DAC make the Nano R4 excellent for analog interfaces. But what is really cool is in addition to the ADC and DAC, it also has a built-in op-amp that can use external resistors for configuration. So if you need an inverting, non-inverting Schmitt trigger or comparator, well, you can do so with ease. At the back, or front of the Nano R4 depending on your outlook on life, is a quick port connector which allows for expanding with other I2C devices. This connector is also excellent for use with Arduino's Modulino nodes, allowing for rapid prototyping. The USB-C connector, finally, USB-C is the world's best programming connector, makes programming easy, and the R4 Nano can also emulate a keyboard and mouse. Honestly, the inclusion of the USB-C alone is absolutely brilliant. For this project, we will build a miniature classic arcade machine that plays a custom-written shoot-'em-up game, which we will call Duo Invaders for legal reasons. This arcade machine will have a left and right button for moving the player and a select button for firing. Two small piezo elements will be used as the speakers, with each speaker being responsible for a different sound, such as a background music and firing. A 128 by 64 OLED will be used as the screen, and a 3D printer will be used to create the enclosure and putting everything together. Instead of using a breadboard, which is ideal for prototyping, we will use a stripboard and raw wire soldering to try and reduce the size of this machine as much as possible. On reflection, I could have made it a lot smaller, but that's still pretty decent. Power will come from the USB-C connector, but because the Nano is upright, we will use a 90-degree USB-C connector so we can get that cable out. This cable will also provide debugging capabilities while also allowing for the creation and development of new games. So it's clear that the Arduino Nano R4 is an absolute beast of a nano development board, but what's a good way to demonstrate its features? Well, this was a hard one because I had to think of a project that would be cool, interesting, and demonstrate the features of the CPU. I've done plenty of IoT sensors, which, let's face it, are not that interesting. I didn't want to do more test equipment, and I certainly didn't want to do any low energy stuff. No, this project needs to show the memory, CPU capabilities, and small nature of this board. What could possibly need lots of memory, operate quickly, and be small? Well, the answer was Duo Invaders. The Invaders game requires a decent CPU speed, plenty of static RAM, as we need a graphics buffer, and timing capabilities for the audio. The graphics in particular are important because of how we will write to the screen. The way that these OLEDs tend to work is that instead of just having an array of pixels in a grid, each 8 vertical pixels is grouped into a single byte, and then these bytes go across the screen in a row. Each of these rows is a single page, and there are a total of 8 vertical pages. What this translates to is an absolute cluster of a nightmare in programming. Sure, compacting 8 pixels into a byte is memory efficient, but by almighty God, it is hard to draw sprites to a screen quickly. If 2 sprites overlap, you have to start bit shifting and masking, and it's just an absolute pain. So instead of trying to save memory, I instead expanded each pixel into its own byte that can rapidly be read and written to in a singular GPU buffer. So this means that 128 by 8 bytes becomes 128 by 64 bytes, or 8 kilobytes of static RAM. Then, when I'm ready to draw to the screen, a simple function, definitely not written by ChatGPT, quickly compresses this buffer to the final GPU data array of 1 kilobyte and then streams this out over the SPI. While this method is memory inefficient, it massively speeds up memory operations during graphics drawing, giving us more time for other things like user input, game logic, and audio. None of this would have been possible with the original Nano. Oh, and just to throw in there a few more things, despite these heavy GPU operations, there's still plenty of time to do things like audio generation, player control, collision checks, etc. So here we have the actual completed arcade machine, and you can see we've got the OLED here. We've got the 2 holes for the 2 piezo buzzers and the 3 buttons on the front, left, right, and fire. Now this whole unit is actually printed out of 2 different parts. You've got the case itself, and then you've got a side panel. So if I just go grab those, you'll see what I mean. What we have is half the case with the side panel off, and this lets us get inside very, very easily to put all the parts in and glue them down. And then once all those parts are in, we can go ahead and glue the side panel, and you have the completed unit. Now in terms of the circuitry, as I said before, I went for a stripboard instead of a breadboard because stripboards are smaller, they can fit in these tighter spaces, we can solder wires, and it's much more sort of rugged as opposed to a breadboard where, you know, things like this where the wires can basically just fall out. By the way, that was the prototype for this design. So all I had to do was grab myself a bit of stripboard. This one's a double-sided, which is quite nice. It's very, very strong, made of FR4. I scored away the parts which I didn't need, snapped them, and then I used a bunch of these types of pin header connectors or pin socket connectors. And then these allow me to pop the R4 in and out. Now you might be wondering, why did I go for this kind of concept? Now some people will be thinking, oh, it's so that he can maintain repairability and stuff like that. And yes, that's kind of true, but the truth is I'm an idiot and I was expecting to break this thing because I am stupid. So by using this, I could pop one of these out and put them back in if I needed to. Now luckily I didn't break any at all. So we can just pop that all together. The wires go straight from the buttons inside, straight to the development board itself with no issues at all. And the only resistors that I have on here are for the buttons, which are pull-up resistors, because these buttons need a pull-up resistor, otherwise it may see them as floating. And that's all there really is to this design. The design for this thing is really, really trivial. We're taking advantage of SPI for the display. We're taking advantage of GPIO for the buttons. They really don't need that much extra hardware, and almost everything you need is on the board anyway. So as you can see, an incredible setup is made from such minimal parts. One extra feature I added was a small right angle USB-C connector. It takes a male, gives you a female, and it puts it at 90 degrees. And the reason for that is because, as you can see here, trying to get a cable in is not going to work. So you can pop this out, slap him into the side like that, and just like that you can push him up a little bit and your design will fit like that. So you can get a USB-C out the back relatively easy without messing around. So here we have the Arduino IDE with the code loaded. Now you can see quite a number of files and it looks complicated, but if you break it down, it's actually rather simple, with the exception of the GPU and how we interface with the screen. Now I'm not going to lie, I did use ChatGPT for this, and the reason for this is because ChatGPT was the only way I could get the screen to work. I tried lots of other examples online, but none of these examples actually worked for me, and honestly I'm not quite sure why. So ChatGPT spat out this code for not only interfacing with the screen, but for packing the larger video buffer into the smaller one. Because remember, these screens store 8 pixels per byte, which means we have to kind of like compress our 128 by 64 bytes into 128 by 8 bytes. And the reason why you want this class like this is so that you can call it and print sprites and characters and data to the screen really easily. So instead of trying to address the individual pixels by going into sub-bytes and nonsense like that, we can just throw it into an array and it gets quite obvious. So we have the invaders.h file, and this actually encodes the actual graphics for each invader depending on what movement they're doing. And you can see that we just defined the pixels as a 0 or 1. Again, the same applies to the player.h. This is just defining the graphics for the player and its missile. And in the audio.h file, this is where we define all of the code that plays music and the fire sound effects. So when you fire a missile, it goes, and if you know, you've got the background music, which is going duh, 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 duh. So it's like the 4 tones that you tend to get from the game that shall not be named. If we go to the actual startup file, the code is really, really trivial. All we need to do is define the left, right, and fire pins and make sure that they're actually enabled. And then we initialize the GPU. And then in our main loop, all we have to do is run level. Now, the level.h file is where the intelligence of this entire program sits. And I'm not going to lie, I probably should have spent a bit more time refactoring and making this code a lot easier to read, because I kind of just slapped things together, as you can tell, until eventually it worked. So yeah. This is not a good example of my coding skills. In fact, it's probably one of the worst. But the thing is, it is simple in how it works, and it should be fairly obvious if you go through it what things are doing. So for example, each enemy is its own little structure, the type of enemy, which tells you what it looks like, which also defines its score as well, the speed of the enemy, and then you've got its position, whether it's alive, and the current animation frame. All of these enemies are packed into a nice little array, which means that we can point of one of 32 different enemies in 4 groups of 8. And if we scroll through this code, you can see that we've got a whole bunch of defines and variables that we're just setting up for this game. Again, enemy missiles, they have their own little structure, defining, you know, their position and whether they're active. And then we have an array of those missiles. And then we've got some code to initiate each missile. And then we've got some stuff to do with flashing timers and player dead. What this is basically doing here is just making the screen flash for a little bit if you die. And here we have the bit mapped numbers for the digits 0 to 9, so we can use this for printing scores and lives. You'll notice it's a 3 by 5 bit map because we have a really tiny screen, so we have to use as few pixels as possible. Then we move on to the code that determines which enemies are going to fire and how they fire, because we want to be able to fire more than one missile from the enemies, but we also want to make sure that it's got some intelligence. So we're randomly picking enemies that are within a certain range of the player and they don't have any enemies below them. So you can't have the top enemy firing, so only the bottom enemies will fire. Then we've got the initialization function for a new level, which is basically determining how everything should be done, including the positions of the enemy, the positions of the player, as well as the score and type of those enemies. And then we come to the most important function, which is actually running the level. And again, it's actually really simple. We simply start by clearing the display to make sure there's nothing else on there. And then we check to see what the current time is, because this is going to be used to control things like missile speed, player movement speed, and whether events happen or not. Then we check to see if the lives are 0, so then we can reset the whole game. And again, we can also handle the player death here as well by checking to see if the player is indeed dead. Now, if the player isn't dead, then we go ahead and run the following code, whereby you move the enemies. And again, it's very, very trivial. It should be quite self-explanatory if you look at the code. Then we move to controlling the enemy motion, which is the motion of the ocean comment here. And what that's basically doing is determining how the enemy moves. If it hits the right screen, it goes down 1 before going left. If it hits the left screen, it goes down 1 before moving right. And that's really, really important. And we split it into sort of like different state machines. So then depending on what's going on, it will then move to the next state. Then we go ahead and display the enemies. We display the player. And then we check to see if the fire button's been pressed, and then handling that if it has been fired. Then we do all the various other functions that the game needs to do, again called as these functions. And then we go ahead and check if the level is completed by looking to see if all enemies are dead. And if they are, we simply create a new level, and at the very end we update the display to show the new game. Now, I highly suggest that you go through this code very, very carefully, because there is a lot to unpack, way too much for a single video, because remember, this is a whole game. But what is really cool is that when you actually understand how this code works, you basically understand how most games work in terms of the basic functionality. It's nothing more than just repeatedly running some level code and then checking to see where the positions of the players are, where their missiles are they colliding with an enemy, how many lives they've got, and then basically doing some actions if those conditions are true. So let's say you wanted to have like a startup menu where you had options. Well, in this main loop, you might have a state machine, and you might say something like, are we currently on the main menu or are we playing a level? And then based on that state, we would then run a different function. So you might run something like run main menu instead of run level. But yeah, you can see that the code is really, really simple. And the Arduino R4 Nano, with its massive CPU and memory capabilities, makes this a possibility. So now that we know how this thing's going to work, it's time for the montage. Let's go.
Takes up half the night. Now there's a Nano, so small, so clean. 32-bit power in a breadboard dream. Nano R4, shrinking it down. Pocket-sized power in a circuit town. Building mini arcades, yeah, we're coding stars. Shooting those mysterious space guys from afar. No resistor hacks, no smoke, no spit. Nano-sized core at 48 megahertz. DAC and ADC, yeah, this board really flies. Yeah. Choo-choo-choo. Wackelwanker. Choo-choo-choo. D. Boop. With a quick port and a USB-C. This little Nano's got a college degree. We 3D print the case, buttons left and right. OLED screen and a piezo beat for fire. Nano R4, shrinking it down. Pocket-sized power in a circuit town. Building mini arcades, yeah, we're coding stars. Shooting those, galactic visitors from afar. Two invaders on the screen. Smooth as butter, coding clean. Arduino Nano R4, you're the king of the scene. Electromaker, yeah, living the dream.
The Arduino Nano R4 is an excellent development board that brings the power of the Arduino Uno R4 into the Nano form factor. Its 5-volt tolerance makes integrating it into existing projects trivial, and the seriously improved CPU and memory capabilities makes it highly usable for all manner of projects. One thing I especially love is that with the higher bit width, increased CPU capabilities, and extended memory, you can use classes and objects without worrying about memory usage, so C++ becomes a real possibility. For those who are looking to go further with the Nano R4, possibly even using in production, the lack of components on the underside means it fits perfectly onto PCBs, and the use of castellated holes means that it can be quickly soldered with ease, while the USB-C and quick port make programming and expansion a breeze. If you like what we do here at Electromaker and want to show your support, then consider hitting the like button, shooting up the subscribe, and hover over to the official Electromaker store where you can get the Nano R4 and all the other bits and bobs you could ever need. This is Robin Mitchell, signing off.